Welcome back to Calculus 1. This is part 2 of our lecture on the derivatives of the 6 trigonometric functions. We're going to jump straight into example 3. Make sure you are comfortable with each of the 6 trig functions and their derivatives. Ideally, you have them memorized at this point. If not, make sure you have them in front of you as we go through these examples. When you're ready, let's get to example 3. Okay, so the question that we'll be answering kind of throughout the next few lectures is still find the derivative of the given function. We're talking about trig functions right now. We still have some other types of functions still to go. Okay, so I'd like to give you an attempt at these. For part A, it's a pretty straightforward quotient rule question. And for part B, we have a product, tangent times secant. Part B is a straightforward product rule question. The only new part is the individual derivatives for sine, cosine, tangent, and secant. That's what we're currently learning about. We're now just combining those with the previously learned product and quotient rules. So pause, give yourself several minutes to attempt these. We'll go through it in about probably 5 minutes. All right, welcome back. Hopefully you're able to get through these. I'm going to kind of get you to think, hopefully, that these are straightforward quotient and product rule questions. The only new part, which you might be struggling with, is knowing the trig functions and their corresponding derivatives. Let's go through part A. So this one's intended to be a straightforward quotient rule question. We're going to think of f, the numerator, as sine of x, and g of x, the denominator, as 1 plus cosine of x. This one's fairly straightforward. The derivative of sine is cosine. The derivative of 1 plus cosine is negative sine. The derivative of 1 is 0, since 1 is a constant. All right, believe it or not, that's it for the calculus. Just knowing those derivatives for sine and cosine, we just now have to combine all 4 of those pieces back using the quotient rule. So let's just plug everything into the formula for the quotient rule. Some of you might be comfortable kind of skipping the work for divide and conquer, but I'll continue to include that within the recorded lecture. Some of you probably find that helpful. So let's just plug in f, g, f prime, and g prime into the quotient rule written there in red. All right, just be careful with parentheses. All right. This one actually simplifies considerably, but be careful. A very common mistake I see is students wanting to cancel the 1 plus cosine of x out between the numerator and denominator. 1 plus cosine of x does not cancel here. And the reason for that is 1 plus cosine of x is not a factor of the numerator. What's preventing that is that negative, that subtraction sign between the 2 terms in the numerator. So the 1 plus cosine of x does not cancel, thinking of something divided by itself canceling to 1, it doesn't cancel out. So we can still simplify this, but by distributing cosine of x through the parentheses. So just be careful, distribute, change the negatives there. Notice we have a minus a negative. And we should get for our numerator cosine of x plus cosine squared. And then simplifying, we get plus sine squared. The denominator is still the same, 1 plus cosine of x squared. All right, now hopefully from the previous part 1 of this lecture, you start to incorporate some of the important identities with squared trig functions. We almost always think of maybe trying to apply a Pythagorean identity. And we can apply that here. Cosine squared plus sine squared equals 1. That allows us to rewrite our numerator as cosine of x plus 1. And now, from the numerator simplifying, even though the order of addition is backwards, now there is a factor of 1 plus cosine of x in the numerator. We can cancel one factor out between the two factors in the denominator, and this actually simplifies, properly now canceling the factor of 1 plus cosine of x. We get as our derivative 1 divided by 1 plus cosine of x. All right, just be careful with the simplification. I see even the best Calc 1 students kind of incorrectly cancel 1 plus cosine of x out, kind of in the middle of the page there. So just be careful. Only cancel factors or common factors. All right, let's go through part B when you're ready. This one is a straightforward product rule question. The only new part are the more obscure derivatives for tangent and secant. Just make sure you know them. The derivative of tangent is secant squared, and the derivative of secant of x is secant x times tangent x. And that, again, is all the hard work. We just now combine the pieces together using the product rule. All right, and since we have some factors there, we can kind of combine them. Secant squared times secant, we can just write that as secant cubed. Tangent times tangent, we can write that as tangent squared. So this actually simplifies a little bit. We can write our derivative for y prime as secant cubed of x plus tangent squared of x times secant of x. All right, make sure you feel comfortable applying the product and quotient rules here. We've been applying them as we would have before. The only new part is incorporating the new 6 trig functions and their derivatives. All right, when you're ready, we'll get to another example. Example 4. We're going to build off of part B here. So definitely make sure you pause to copy this work down if you didn't get through it yourself. When you're ready, we'll move on to example 4. Okay, now let's go back to a question we haven't maybe talked about in a while. Let's find the equation of a tangent line. Okay, and this one might look familiar. It is basically part B from the previous example. So we have here our answer from example 3, part B. The derivative, y prime, was secant cubed of x plus tangent squared of x times secant of x. Now, the only thing that changes here is our function isn't called y, but it's called f of x. So if our function f is tangent of x times secant of x, well, we can just make use of our work from example 3b to calculate the derivative f prime. And why do we need a derivative? Well, just think, how does that relate to the question, finding a tangent line? Recall our question, what is a derivative? Slope of a tangent line. So we need the derivative since that represents the slope of our tangent line. All right, so the work here might seem simple since we're kind of using our work from example 3b. All right, and again, it might have been a while since so you recall the equation for the tangent line. Y minus f of a equals f prime of a times x minus a. Here, the value of a which represents an x-coordinate at which we're finding the tangent line. Given in the problem, that value for a is pi over 4. So we have our equation here, y minus f of pi over 4 equals f prime of pi over 4 times x minus pi over 4. All right, now at this point, the calculus is done. We basically did all that in example 3b, applying the product rule to get this derivative, f prime. But the rest of this is sometimes tricky for students since they kind of forget a lot of their basic and foundational trig from their pre-calc course. Now, what we actually need to figure out are what are the values for the function f of x when x equals pi over 4, and then the value for the derivative f prime of x when x equals pi over 4. All right, now how are we going to do that? You could either think back to the unit circle if you know that. I prefer and advocate using one of the two special triangles, which is equivalent to the unit circle in the first quadrant. So I'll pause, give yourself an attempt at this. At this point, the problem really comes down to being able to find the values for tangent and secant of pi over 4. We'll check in maybe 30 seconds. All right, now how do we get the values for instance, let's start with tangent. How do we find the value for tangent of pi over 4? Just think from basic SOHCAHTOA. Tangent of an angle is the opposite side divided by the adjacent side. So we just go to one of those angles, pi over 4 radians. So let's go to the one in the lower left. The opposite side is of length 1, and the adjacent side also of length 1. So we should get tangent of pi over 4 as 1. Secant of pi over 4, secant is not one of the three basic trig functions, sine, cosine, or tangent, but we can think of it as a reciprocal of cosine. So if you apply SOHCAHTOA from your triangle here, you should be able to find that cosine of pi over 4 is 1 divided by square root of 2. You might know that in the equivalent rationalized form, square root of 2 divided by 2. And if we just plug that in, notice now we have 1 divided by 1 over square root of 2. Divide by a fraction, multiply by the reciprocal, and we get secant of pi over 4 comes out to just square root of 2. All right, we can make use of these values right up above. And what we should be able to find with a little simplification for the derivative, we should be able to find that f of pi over 4, plugging x equals pi over 4 everywhere within the function f of x, we get that value as square root of 2. And then plugging in pi over 4 to the derivative, which is a little bit more work, that all simplifies to 3 times square root of 2. And at this point, we just plug all that into the equation of the tangent line written just below there, and we get our answer here in what seems to be very minimal work, but again, we did most of the differentiation that was found in example 3b. And then also here, recalling some basic trig, SOHCAHTOA, basic trig values, that was the other kind of place we did a little bit of work. All right, so again, make sure you thoroughly understand this. This part 2 of this lecture, in terms of time, seems rather short, but it's very dense. All right, when you're ready, we'll take a look at one last final example, example 5. We'll tie this into the previous lecture, thinking of derivatives as rates of change. All right, when you're ready, let's get to example 5. All right, so this will build off our previous lecture, derivatives as rates of change. And now we can start incorporating pretty much everything from the course so far. For this question, example 5, we're given the position of an object. We're still going to use the same notation. We'll usually denote the position function as s of t. Here it's given as t times sine of t. So times a product. We're going to use the product rule here. And what the question wants is, given the position of the object at a certain time, find the object's acceleration. All right, now what we just need to know for our Calc 1 course, physics and kind of calculus complement one another. So if you have yet to take a physics course, I'd recommend taking one, if you have to, soon after taking our course, while our course content, Calculus 1, is still fresh. The only thing we need to know is, given position, the acceleration is the second derivative of position. So this one, it's going to be a little bit of work, but it's, again, a straightforward application of the product rule. We just have to calculate first s prime, which would represent the velocity, and then differentiate that yet again to get the second derivative, s double prime, which would represent acceleration. Now, I'd like you to try this. This is a good question, in my opinion. It's not too difficult, but there's a lot of ideas that we previously covered coming together. All right, so pause, give yourself, I would say, probably several minutes, 2, 3, maybe 4 minutes. Take your time, apply divide and conquer, and just make sure you start knowing your derivatives for the 6 trigonometric functions. We'll check in several minutes. All right, in case you're stuck, let's just go through the first derivative, s prime, which would be velocity. We're going to apply the product rule. At this point in the course, now that we're, kind of getting into the real, bulk of the course with differentiation rules, we might start to not write down divide and conquer or work like we would have before. Hopefully you can apply the product rule as you go. Okay, so we're going to differentiate first the first function, t. That would differentiate to 1. The second function stays the same. And then we keep the first function the same, but differentiate now sine. The derivative of sine is cosine. All right, hopefully that is okay. We're just going to clean this up a little bit. We don't need the multiplication by 1. And we can write s prime representing the velocity as sine of t plus t times cosine of t. And what we have here in the velocity, s prime, is another product. So to get the acceleration, differentiating one more time, apply the product rule yet again. If you kind of got stuck earlier, maybe see if you can finish with this as a building block for your work. See if you can now differentiate s prime to get s double prime. We'll check in about a minute. It's a very similar calculation with the product rule. All right, hopefully you were successful. Let's check. Notice we're not just applying the product rule here. Sine of t, we can just recognize the derivative of sine of t as cosine of t. The product rule is only needed for differentiating t times cosine of t. All right, and if we apply that again without using divide and conquer, the only new part here is being careful. The derivative of cosine is negative sine. And that's pretty much it. We can simplify this a little bit, and we can express our final answer for the second derivative, which physically represents the acceleration. We can write that as 2 cosine of t. That's adding the 2 like terms of cosine of t, and then minus t times sine of t. All right, hopefully that went well. We're going to start to see some of these questions, position, velocity, and acceleration start to come back as we get access to more differentiation rules. And there are more still yet to go for the course. We have product and quotient rules covered, but we have yet to get to arguably the most important one, called the chain rule. That'll basically be coming up within the next lecture.